Actually, yes, this work has been done while I was still at Yahoo, and it is a, let's say, collaboration between the four of us, like Gabriele, myself, Andrew Haynes, and Munyal Almas, all of us from London. And yes, I mean, as I said, this has nothing to do with Facebook, which is my current affiliation, but it's mostly a technique that we developed for Yahoo. And in particular, we are dealing with prediction models. And, just to make an example, not very, let's say, funny one. I mean, let's consider a medical record of a person, and let's consider, a set of features extracted from the medical record. And as you know, you can take this set of features and you can train classification models. And I'm pretty sure you're all familiar with this, given also the nature of the track. And, it is well known, or at least everybody, continually says that, most of the effective classification models and machine learning models are like black boxes. You don't really know why they're working, but they work pretty well. And, you feed this sample into a machine learning model, and you basically get in return whether the person might, is healthy and living well, or, it might not be so healthy and not living so much well. So actually, the goal of this work is try to take the prediction model and to understand why the outcome was a negative one. And we will do that by analyzing basically the content of but let's say by pre-processing the content of the black box, in this case, the machine learning model. And, all right, sorry, anyway, the content of the machine learning model, and we'll try to take a particular sample and explain why that sample was classified as negative by giving also a possible explanation of how to modify, to tweak that sample in order to make the classification model to classify it as positive. In this particular work, we focus on tree-based models, and in particular, we focus on ensemble of trees. And these has been regarded as being very, very powerful, for instance, random forest or GBDTs, but also not very interpretable, as opposed as traditional decision trees, which are instead very, very interpretable. And when I say that they are not interpretable, I say that because usually the size of the model is huge. I mean, in practice, like practical models are like in the orders of thousands of trees. So the size is in the order of thousands of trees. So some preliminaries. As I already said, we are focusing on classification problems. And in particular, we will be focusing on a binary classification problem, but the extension to multi-class is not difficult, I would say straightforward. And we are not actually dealing with regression models. The definition itself is a little bit trickier because you don't know how to define actually a positive outcome, something above, or it's kind of tricky also to define the problem. And for the rest of the talk, we are considering an n-dimensional real vector space, and we are considering features made up of samples made up of n features, and basically we represent each object as a feature in the n-dimensional vector space. And again, we are dealing with a binary classifier, so labels are +1 or -1. Another thing is that, as I said, we focus on ensemble of k trees, so we are considering a classification function that is basically a function of k weak learners. In this case, each weak learner is a decision tree. And let's say each learner is learned on the basis of a subsample of the sample space X. And without loss of generality, we assume that the final predicted label is basically the sign of the sum of the outcome of each learner separately. So you basically take the majority voting. Okay, so again, our problem intuitively is we take a sample that has been classified as negative, and we find a way to transform it. Now the slide is not, the sample is the same, but just the color changes. But anyway, so we try to find a way to transform it in a way that the sample doesn't change too much, but the outcome of the prediction model is actually now positive. And as we'll see, this is driven actually by the real problem. And more formally, we are trying to find, among all the possible tweakings of the initial sample, we want to find the one which is not too distant from the original one. And that delta function over there is our distant function. It's, you can, in this work, it's not really, it's kind of flexible with respect to this distance function. And as we'll see, we have tried some of them. But basically, it's important to understand that the user of this framework can actually say, okay, I don't want the initial sample to change too much. We'll see actually that you can actually put also some constraints on each feature separately. Now, how does it work? Okay, so let's consider, for instance, for a moment, a single tree in the ensemble. Let's take our negative sample and let's find the path that is actually leading to the negative outcome, right? So now what we would like to do is to take the tweaked sample and find a way to actually modify the features so that now the new path is actually the positive one. And of course, we want to do it for all the trees, or the majority of the trees, in fact. So for the moment, let's focus only on the trees that were resulting in a negative outcome. So among all the trees that we have, let's just focus and let's just consider the negative ones. And now, for each tree that led to a negative label, let's consider all the possible positive paths in that tree, right? So we take the tree that was negative in our ensemble, and let's consider all the positive paths, and let's discard the negative ones. Now, as you can imagine, if we could turn that tree from negative to positive, that could be already a step, let's say, towards our final goal. Of course, needless to say, if we are not dealing with an ensemble of trees, you can always find the optimal change, provided that it exists, you can always find the optimal, let's say, tweaking for the sample just by analyzing the positive the positive paths and actually tweaking the sample according to the features in those paths. And we are putting actually an additional constraint on the possible modifications that we are allowed to do. That is, each feature cannot change by more than epsilon. So we are looking to modifications of each feature in, let's say, plus or minus epsilon. So, for instance, if you have, I don't know, the length of the text, we are not allowing the text to double or to half. We only allow the text to increase by, by 2 lines. Just to make an example. And of course, we can do it. We do it for all the features. In fact, a trick that you can actually apply is you can standardize each feature and you can just set an epsilon value for all, the same for all the features, the same constraint for all the features. Now, in addition to that, actually what we do is we are not going and work directly on the sample, but instead we focus on the tree itself. So instead of starting by tweaking the sample, we start by building for each tree a set of possible candidates of epsilon satisfactory instances. And the way we do it is that we take all the possible features and we basically compute the farthest, the most admissible instance starting from that path. In practice, you take a feature, let's say xi, and you take the threshold for that feature in the path, and if the threshold is theta I, you just, and the condition is like xi smaller than or equal to theta I, you just subtract epsilon. So basically, you are moving the threshold towards your final goal. And you know that the best that you can do is to move it by epsilon, because otherwise the new sample will not be epsilon satisfactory. And symmetrically, you can do the same for conditions like xi greater than theta I. Now, we have reverted the problem. That is, we are instead of tweaking the features, we are just building a set of admissible epsilon satisfactory instances. And now we do this for all the negative trees. And what do you do now is that among all the possible candidates, what you do is that you try to find the closest to the initial sample that was negatively labeled. So again, just to repeat, you take all the possible trees, you build for each positive path in each possible tree a set of a candidate, which is an epsilon satisfactory instance from that path. Now you have all paths that are actually positive and that they are actually epsilon feasible. Now what do you want to do? You want to take your initial sample and you want to find the closest one to this set of candidates that is also, of course, epsilon satisfiable. So we have reduced the problem from, let's say, tweaking the features to the problem of finding the nearest neighbor of a set of candidates that can actually be computed offline, because you can do it, of course, for a set, let's say for a fixed epsilon value, you can compute it offline. And so basically the problem is to compute the x prime that minimizes the distance delta. Now, okay, needless to say, even in this formula, let's say form, the problem is NP hard. It has been already shown in the past. Let's say a relaxed form of, let's say a less constrained form of this problem to be reductible to DNF maxat. And anyway, intuitively, as you can imagine, you have an exponential number of paths for each tree. And so, you might have to actually explore an exponential, an exponentially big candidate set. So that's the intuition behind the fact that it's kind of feasible. But in practice, as you can imagine, you can always have, in practice, the number of let's say, positive paths are, not as huge as you would not like them to be. So far so good. This was let's say, the description of, or better, the intuition behind the solution that we found and the description of the problem. We ran some experiments as well, and in particular, the motivation for the talk, for the study itself, was a practical motivation. Let me go to this slide first. So the practical motivation was to, let's say, help advertisers to, let's say, better build, their advertisements. That is, we want, for some clients of Yahoo that were seeing their advertisements continuously rejected, or better, not selected by our system, we wanted to explain to them why, and also maybe to give them some suggestions on how to improve their let's say creatives, the appearance of their advertisement. So we basically took a random sample of about 1,500 ads that were actually, from customers, from Yahoo customers, and those were ads that were actually served by the mobile app that Yahoo had. Yahoo Gemini was a project in advertisement. And we actually selected the sample, it's not really important, but basically there were 50-50, a 50-50 split. 50% positive and 50% negative instances. And for us, positive meant high quality, that is visually appealing, and whenever the user, whenever a user landed it on that ad, the user would have spent time on it and would have enjoyed the ad. And negative was the opposite, that is, a user landing on those ads would bounce immediately back because, they didn't find useful. Then, in order, our classification model, the one that from which we started to build the explanations, was a GBDT-based classifier and a random forest one. And actually, we tried also other alternatives, but random forest and GBDT were the ones with highest, let's say, accuracy, let's say, of the system. And we ran several experiments, of course. So, as I said, the goal was to kind of suggest advertisers how to make their ads better looking. The one that you see, it's a real example. The initial ad was kind of, so that's the landing page of the ad. It's not the ad that you see that you click on. Is after you click, you land on that page. So the initial version, the red one, was actually not performing very well. And by looking at the result of our method and also by discussing with creative strategists, we actually agreed that the reason why was that it was too long and the title was bad and it was not appealing. So by actually following the suggestions from our model, we actually were able to make it better. And those are the features that we are using, and no surprise. I think they are not surprising. We are considering the text length, the number of pictures, the number of edit boxes and stuff like that. Now, the first experiment that we ran was like the coverage, to measure the coverage of our system. So as you can imagine, by varying the epsilon value, you cover more or less advertisements. And as you can see, by setting epsilon to 0.5, you're actually covering almost 77.4% of the negative ads. That is, you're able to generate recommendations for almost more than 75% of the ads, of the negative ads. And of course, it also depends on the ad. On the, I don't know if you can read it. Unfortunately, I was expecting a big screen and whatever, but anyway, so basically, I'm not even able to read it. So basically, as you can see, by varying the value of epsilon, you see how the amount of possible tweakings that the system is returning. Of course, those are the number of features those are the possible features that you have to tweak. In most of the cases, ads are really, really bad, and basically you have to change them all. Then we also try to evaluate, so especially this amount of modifications is reflected on the cost or distance function, so how much you should tweak your ad. And again, varying epsilon, we measured it. And as you can see, by increasing epsilon, of course, you are more loose and you allow more modifications, and of course you allow more things to change, and the cost increases. We tested 5 different distance functions, and they are the usual suspects. Euclidean, cosine, Jacquard, Pearson, and also we also tried to, again, a distance that was basically the number of features that you had to tweak, and that was the most appealing one. We also ran a qualitative evaluation. That is, we had a team of creative strategists to evaluate the suggestions, and we asked them to let's say rate them as helpful, non-helpful, or non-actionable. Of course, only on bad ads. And let's say we were positively surprised to see that almost 60% of the recommendations were let's say rated as helpful, and with also high agreement between strategists, and only 0.4% were non-actionable suggestions. For the rest, let's say they were deemed to be non-helpful, or something like, okay, this is clear, this was naive, this was clear. So also, they said that they were not helpful, but it was not a mistake of the model itself, of the technique itself. And in general, you can also try to understand the helpfulness of features by looking at how those features were involved in deciding whether the suggestion was helpful or not. And here, for this specific case, we did this analysis, and for instance, we discovered that the most helpful suggestions were on the length of the text, the number, for instance, of images, the number of entry boxes, and stuff like that. And to conclude, actually, we have provided a formal definition of a problem, whose solution is actually the interpretation of the model itself, because we are providing justifications, or better, we are providing modifications to an original negative sample in a way that also can explain why the sample was classified as negative. So you're actually showing the features that led the model to think that let's say the sample was negative. And we tested our method on a real data set, and we asked professionals to evaluate the effectiveness, and in practice it worked pretty well, because about 60% of the recommendations were actually judged as useful, and for that values of epsilon and the cosine distance function was used. And that's it. Thank you.
Thank you.